Hello, welcome to Mathematics with Simon. I'm Simon. Today we're going to look at the hypernatural numbers and more broadly non-standard models of arithmetic. So somebody who was watching the video on filters and ultrafilters was very nice about the video and mentioned that they were studying hypernatural numbers. So we thought, let's do a video on that. That'll be fun. I studied this a bit for my PhD, and for my master's degree this kind of stuff came up. So what are the hypernaturals? They are a set of objects. Actually, these objects are sets, relations and operations that satisfy the axioms of first order arithmetic. But they're not isomorphic to the natural numbers. They do not obey the principle of induction and the well-ordering principle, which are of course logically equivalent to each other. They're a subset of the hyperreal numbers. The hyperreal numbers are important in many ways. For example, they let us carry out calculus using infinitesimals. So we're going to take a look at the ultra-power construction of the hypernaturals. Actually, a similar construction works for the hyperreals. But there are lots of different hypernatural constructions and also non-constructive proofs of their existence. For instance, there's one using the compactness theorem of logic, which I can explain if people want me to. I'll do a video on it if people want me to. Anyway, let's look at an example of the hypernaturals. I'll do any video people want me to do. I mean, I'm not sure about a version of Wrecking Ball or anything like that, but basically, maths, I'll have a go at anything. So, we start with all sequences of natural numbers. We choose, this is constructing the hypernaturals, not singing Wrecking Ball. We start with all sequences of natural numbers. We choose a non-principal ultrafilter on the natural numbers, and the axiom of choice shows that these exist. Addition is component-wise, and two sequences are equal if the set of components that are equal falls into the non-principal ultrafilter. So basically they're equal if almost all of their components are equal, where almost all is defined as being a member of the non-principal ultrafilter. So this contains the natural numbers as a subset, which we'll show, and it has a lot of the copies of the integers above it. And we can see why the structure does not follow the well-ordering principle, because if we choose a bunch of elements of the integers, that set, if it's an infinite set, may not have a least element. And also, induction is not able to jump from the naturals up to these copies of the integers, whereas induction can run through all the naturals. It can't jump into the integer sets. Okay, so how does this look? So basically, you've got all of the ones maps to 1. So the equivalence class of the string of all of the ones maps to 1. So for instance, in that equivalent class, you could have something that goes 2, 1, 1, 1, 1, 1, 1, 1. That's fine. That just is still mapping to 1. The equivalence class of the string of all the 2's maps to 2. The equivalence class of the string of all the n's maps to n. But then 1, 2, 3, 4, 5, 6, 7 is greater than the equivalence class of any integer, because for almost all of the components they will be greater than n for any n. So this is a sort of plays the role of something that's bigger than all the integers. And then 2, 3, 4, 5, 6 is bigger than 1, 2, 3, 4, 5. And 1, 1, 2, 2, 3, 3, 4, 4 is less than 1, 2, 3, 4, 5, and 1, 1, 1, 1, 1, 2, 2, 2 is less than 1, 1, 2, 2, 3, 3. And if we think about this for a bit, we can see how rich the structure is and how many options there are and how many kind of equivalence classes could be built. So non-standard models of first order arithmetic do raise some philosophical questions. And I think it's a kind of challenge for the structuralist view of mathematics, and we'll see why. But before we get into that, we're going to just define structuralism and constructivism. So structuralism, in a structuralist view of mathematics, mathematical statements are objective. Objects have meaning relative to their position in the structure. So the whole content of the number 3 is its relationships with 1, 2, 4, 5, 8, etc. If you want to understand 3, you need to understand its place in the naturals. Mathematics is about structures and the homomorphisms between them, the structure-preserving mappings between them, and ZFC, ZF set theory with choice, is basically the foundation of mathematics under a structuralist view of the world. although some want to use category theory, and I have some sympathy for that view. But most people think of it as ZFC. Constructivism, so intuitionism is a certain brand of constructivism in which mathematics is built in our own minds, and so it's subjective, not objective. But there are versions of constructivism that are not intuitionism. Mathematics is kind of about constructions. Actually, if I'm going to put about in quotes on the left, I'm going to put about in quotes on the right. Mathematical existent proofs consist of a construction of the thing that you're showing exists. So the kind of existential qualifier in mathematics corresponds to the fact that you can make a construction. And that kind of means that you can't have excluded middle, because you can have a situation where you can't build something, but you can't constructively show it can't be built. So the foundation could be intuitionistic logic, which is basic logic without excluded middle. Or some constructivists want to use ZF without choice. I think there's a feeling that choice is quite non-constructive. So that's the kind of difference between those two broad methods of thinking. And so having alternative models of first order arithmetic is a problem, because I might worry that I don't have the same model in my head as you do, and the constructivists would be less worried about this. But if we're structuralists, we might care that we might have different models in our head. If I just describe it to you in terms of the first order sentences, how do we know that we've got the same model in our heads? So one way around this is to present the natural numbers as a second order theory. So for instance, that would mean that we do have induction, because induction is a kind of second order statement, because it's about sets, isn't it? And the well ordering principle is about sets. Problem with this, actually, or a problem with this, is the Scollon paradox, which basically shows there are countable models of ZFC. They look countable to us. But if we use the diagonal argument inside the model, we can find an uncountable set within the model. So how can it be there's an uncountable set within a countable model? Well, the reason is because this countable model is really small, so a bunch of mappings are missing, and uncountability is about the non-existence of a mapping. So we can prove that a set is uncountable within the model because that mapping's missing. But this is kind of a resolution, but it's not entirely satisfactory, because it shows that being uncountable is a relative concept. You're kind of uncountable from within the model, but countable when looking in from outside, which is odd. So there are some real complexities or even weaknesses around structuralism. On the other hand, the constructive view does make a lot of mathematics unavailable, because it means you can't prove, you can't do proof by contradiction or reductio. So I think my PhD supervisor, Moshe Makova, I think his view was the key is to understand the interplay between the two, I think, which is brilliant, and to say that we have a preference for a constructive proof because it has more content, because it shows you how to build the thing. But structuralist arguments still have merit and value, and we can just appreciate both, and that's really, I think, a very positive way of looking at it. There is another way out, which is sort of the mathematical Platonism of Kurt Gödel. So Gödel believed that their set theory was objective. These sets kind of existed in a similar way that the real world exists, and so what we need to do is develop our intuition about them and learn, and there's a kind of right answer for things like the continuum hypothesis and the axiom of choice, and there's a correct model for the integers. And I suppose we echo that sentiment when we talk about the standard model. That is the correct model. So mathematical Platonism is another way, and again, it shows that all of philosophy is footnotes to Plato and Aristotle discuss. I don't really believe that, but I think what I do believe is that Plato and Aristotle were very influential and had a lot of good ideas early on. So anyway, that's another way out of it. So there's various ways to make yourself comfortable with this, but foundations of mathematics are not simple, and the kind of non-standard models of arithmetic are quite a window into that. I hope you've enjoyed that. If you have, please hit the like button. Please do also subscribe and hit the notification bell. I'd love to hear more of your ideas, and I hope you enjoy your mathematics.